Hi. Today we'll talk about chapter 6. So we finished chapter 5. And if you remember, chapter 5 was about Newton's law. Newton's first law, second law, third law. And we had applications of Newton's second law on an object moving in space, an object on an inclined surface or a flat surface. In this chapter, chapter 6, we are not going to cover the whole chapter. We just take one application, so it's a short part. In the textbook is 6.1 only. It's applications of Newton's second law in circular motion only. So we take applications of Newton's second law in circular motion only. Now, if I take you back to Newton's second law, you remember we said F net equal mass multiplied by acceleration. That's Newton's second law, which means now, when there is acceleration, there must be a total force on the system or on the mass. Or when you have a total mass, there is an acceleration. Let's go back to circular motion, which we covered earlier on. In circular motion, this is the center, and this is a mass, velocity vector, and this is the radius. So it could be here, or here, or here. Let me change the pen. Now, what did we learn in uniform circular motion? If you remember, we said in circular motion, uniform circular, you have an acceleration always towards the center. What did we call it? A sub c, eh? So, if we have acceleration, what we must have? According to Newton's second law, a total force. Now, which way is AC? Always towards the? Which means now I must have a total force always towards the center. So at this point, there is a total force towards the center. This point, total force towards the center. This one, this one. At any point, there is a total force towards the center. This total force towards the center, we, instead of calling it F net, because it's towards the center, we call it centripetal force. So we have an F net equal a force called F sub c, centripetal force. This centripetal force is not an external force on the system. No, it's the total from the system itself, all the forces in the system. Yeah, so you have to think, what are the forces on the mass in the system? Find their total, and the total must be always towards the center. This total force, we call it centripetal force, force towards the center, Fc. So at this point, there is an Fc, yeah? This point, Fc, 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 and so on. Centripetal force. Now, back to F net. So I can replace F net by Fc in centripetal circular motion. M. Acceleration here. We have a name for it. What's the acceleration? AC. Centripetal acceleration. So this is the formula for finding the centripetal force in the circular motion. But don't forget, Fc is a total force towards the center always. Now, if I replace AC, what is AC? Is V square over R. So what is Fc equal to? mv square over R. Now, out of this, we reach the point to say that whenever we have a circular motion of an object, there must be a total force towards the center, always. This total force towards the center is not an external. It's not you add another force to the center. It's within the system itself. Find all the forces on the system, and the net will be towards the center. If you don't have a net towards the center, you cannot create a circular motion. So look at it in the other way around. If you want to create circular motion, what do you need? A force towards the center. Yeah? A net force towards the center. So in any circular motion, you always have a total force towards the center to give you the circular motion. And this total force, we call it F sub C, centripetal force, M A sub C, or mv square over r, circular motion. Now, let's take an example of a circular motion, which we all know. Think of the Earth and the moon. What does the moon do? Circulate Earth in a circular motion. Yeah? And this is the radius. So do we have a circular motion or not? Now, when you have a circular motion, there must be a total force towards the center. So here there is a total force on the moon. Okay? Now this FC towards the center comes from within the system itself. So now you have to think, what are the forces of the moon? What are the forces of the moon? Do we have a force on the moon or not? What's the force? F, gravity force, yes? Which way is gravity force? So do I have a force towards the center or not? Yeah? Now, putting it this way is not right. You put Fg and Fc. It means there are two forces, yeah? No. Fg is the only force towards the center. So what's the total force now on the moon? And this is Fc. So in the case of Earth and moon, what do I say? Fc comes from force of gravity. Which means if there is no gravity between Earth and the moon will not circulate Earth. It goes on. So the gravity gives it the circular motion. Now if I want to substitute, what is Fc? Mass of the moon, speed square of the moon, over the radius, distance, center to center. Force of gravity on the moon. There are two ways here. Force of gravity means weight, yes? It means the weight of the moon on Earth. Think of the moon as a person, yes? What's the weight of the moon on Earth at this distance? It's mg. But which g? Not 9.8. G at this position. So g of the moon, here. And remember, g changes, yes? Gets smaller and smaller the farther you are from the center of Earth. This is one way. Or think of the force of gravity from school. What do you have? You have a general constant, mass of the Earth, mass of the moon, square. Same. Now what we want to say here is that the moon circulates Earth because there is a centripetal force towards the center. Where does it come from? This F net comes from gravity force only. No other forces. Are there any other forces on the moon? Okay. Let's take another example for a small thing. Think of the atom. We have the nucleus, and in the nucleus we have protons and neutrons, yeah? And outside we have electrons. And the electrons circulate the nucleus at a radius r. Yeah? Do we have circular motion? Yes. So what we must have here to create a circular motion? A total force towards the, and this total force is coming within the forces in the system itself. Now think, what are the forces on the electron? Do I have a force? No, Fc is the resultant, yeah? But I want to know where does it come from? Magnetic? This is magnet? These are magnets? What are these? Charges, yes? So what type of force do we have? Electric force, not magnetic force. Attraction. Which way is the attraction? Towards the center, yeah? So this is what? F electric. And this F electric is what? Fc or F net. So what do I say in this case? I say Fc comes from electric force. No other forces in the electron. And Fc, m of the electron, speed square over radius for the electron. Electric force, of course, you find it by Coulomb's law. This is in physics too, but I just write the formula. Coulomb's constant, charge of the electron, charge of the all protons, n protons, because it's not just one proton, over r squared. So in this example, we found that the centripetal force comes from electric force. This example, gravity force. These are two general questions. Now, let's take specific examples of circular motion, which we need in this course. Let's first talk about, now here, this section is divided into two parts. We have two types of circular motion. The first type of circular motion, we talk about horizontal circular motion, horizontal. Examples of horizontal circular motion. And the second part is about vertical circular motion. Now, when you have vertical circular motion, look, the plane of the circle is in the direction of gravity or not? So you include the gravity. But when you circulate horizontally, gravity is not in the plane of the circle, so it's nothing to do with the gravity. Okay, so we'll take the first one, horizontal circular motion. The first example of horizontal circular motion, I can show you here. This is a mass, a ball, and this is a piece of string attached to it. I can create a circular motion either vertically or horizontally. Yeah? Now in this part, which one I want? So let's talk about the horizontal. Now if this one turns around in a horizontal circular motion, what do I have? Circular motion, yes? So I must have a total force towards the center. What's the name of this total force? Centripetal force, yes? Fc. Now, where does it come from? Let me draw it here. Of course, if you draw a circle here, it doesn't show if it's horizontal or vertical. So the best way to say horizontal, put it inside the frame, like you have a table, and the circle on the table, then it becomes horizontal, yeah? Looks like horizontal. This is the mass, and this is the center. Now, in this case, what are the forces on the ball? Tension. Gravity, but gravity is not in the direction of the motion, so we don't include the gravity. So how many forces do I have towards the center? What's the name of the force? So how much is Fc? Equal to? Tension. So here I have the tension towards the center, Ft. At any point is Ft. Yeah? So when I have tension horizontal, I can say that Fc equal to force of tension in a horizontal. This is an example of a circular motion, horizontal circular motion. Now, What is Fc equal to? mv square over r equal ft. Generally speaking, Fc depends on mass, speed, and radius, yeah? Now, in this case, now, if I increase the speed, what increases? First, what increases? Fc. Because Fc and v square are directly proportional, yes? So when you increase v, you are increasing, and when you increase Fc, you are increasing the tension, yes? Now, if I increase the speed more, what happens to the tension? But can it go forever? Increase? You reach a point? Snatched, yeah? Breaks. This is the maximum tension it can take. It depends on the material, yeah? That's if you change the speed, increase it. What if you change the radius? If you make the radius bigger, what happens? Decreases, yeah? Then the tension will be less. But if you make the radius smaller, so the tension will be higher. But at the end of the day, Fc equal tension. That's the first example. The second example of horizontal circular motion, it's about roads, the normal roads we have. We have two types of roads. The first type of roads, we call it unbanked road. Unbanked road. Unbanked means the road is leveled, plain, it's not angled. So if you have a car on a leveled road, unbanked road, you're driving straight, and then suddenly you turn to the right, or you turn to the left. This is part of circular motion. Or you just enter a roundabout to do circular motion, yeah? So let's say this is a main road, and then there is a bend on the road. Not necessarily you complete a circle to have circular motion. Any turn is part of a circle. So this is part of a circle. And this is the radius, r. And this is the car here, going this way. Velocity, tangent. Do we have circular motion here or not? The car is doing circular motion, part of circular motion. Now, if the car does a circular motion, there must be a total force towards what is the name of this force? Centripetal force, Fc. And this Fc, again, is not an outside force, it's within the system itself. Where does this force come from? Let me show you this one on the table. Think of the table as a leveled road, yeah? Unbanked road. And this is the car. Yeah? Of course, there's no cable on the car. This is just to keep it on a circular motion. And think this is part of a roundabout or part of a bend. When the car does turn, yes? This is circular motion. Okay, now we have to think, we have to find a force, at least one force towards the center. Otherwise, the car will not turn. How many forces on the car? You know.
Normal force.
Normal force is opposite Fg, yes? Okay, now here, vertically, Fg down, normal up. Now these forces, are they in the plane of the circle? So those are out. We need forces in the plane of the circle, yeah? Now, friction, okay, friction usually is opposite motion, yeah? So, if the car moves this way, where is the friction? This way. Is this direction towards the center, I need a force towards the center. If you don't give me a force towards the center, I cannot turn the car. What makes, no, it's not. Acceleration is related to a force. We know for sure there is a force towards the center, because if there is no force towards the center, you cannot make a circular motion using your car. Yes? But we are asking here, this force, what's the name of this force? Where does it come from? Now, we said, if you mean this friction is this way, yeah? So it's not in the direction of the center. I need a force this way. Your answer is right and wrong. The answer, friction, is right, but the friction you're talking about is wrong. The friction you're talking about, it's in the opposite motion, yes? But this is not in the direction of the center. So what do I need? Yeah?
Doctor, doesn't the direction of the force of the car itself, once you make like this?
Okay, that's a good point. He says that the car turns because you are turning the steering wheel, yes? You're turning the wheels. Yeah? Now, okay, let's say, which means that you have the force coming from the wheel. Now, let's put your car on ice. And you drive straight, and then you turn to the right or to the left. Didn't you turn the wheels to the right or to the left? What happens? Your car will do circular motion? What happens? Cannot. So it means the force of turning is nothing to do with the centripetal force. The turning here just to turn the direction, but not necessarily gives you the circular. You need a real force towards the center. This force is responsible for the circular motion, yes? Now, what you said the friction is right, but you gave me the wrong friction force. There is another friction towards the center. It's friction sideways. When you drive a car and you are on the turn, don't you feel your car wants to slide in and out towards the center? So we have friction in the direction of the center, yes? That friction is responsible. Not this friction in the direction of motion line. Yeah? It's wrong. So we have two friction. This friction here, this is not the FC. This is opposite motion. Yeah? Of course, this will work when the car brakes. When it turns, it doesn't work because it's different. It's called rolling. But we have a friction this way on the tires. The four tires, they want to slide in. When you turn the car, you feel that there's a friction sideways. So what we say, FC comes from what? Friction sideways towards the center. So now this force is towards the center, then it's equal to FC. Now FC equal a friction force. But remember, I don't mean this, I mean this one. Now let's replace them. What is FC? M, V square over. What is M? Mass of the car. Speed of the car, radius of the road. Friction comes between the tires and the roads, yeah? What's friction force equal to? Mu multiplied by normal force, yeah? Look here. What is the normal force equal to here? Equal N, yeah? So here we have Fg equal normal force, which means in the drawing is towards you, yes? Normal force. And N, Fg down. Now replace the Fg. Mg equal N, yeah? Now let's put N here. We'll have mv square over r mu multiplied by mg. Do I need the mass of the car? Look on the both sides. Which means the mass has no effect on the circular motion. regardless of the mass of the car, big car, small car, bicycles, bike, it will follow the same equation. The equation does not depend on the mass. What is left here? If I write it here now, you'll have v square equal mu r g, and v root mu r g. So when the car on an unbanked road, the friction sideway equal centripetal force. Those are equal. If they are not equal, what do you feel that you will be able to do the 10, or what happens to your car? Slides off the road, yeah? Now, why slides off? Because of this equation. This equation is talking about the speed of the car on the bend. It says if the speed equal to mu, what is the mu? Coefficients of friction between the tires and the road. R, radius of the bend or the roundabout. G is the gravity acceleration. This formula gives you the maximum speed you can enter the roundabout or the bend without any slipping. Yeah? The car will stay on the road. It will not slide off. So, before I give you numbers here, let me take you to mu here, because deliberately, look, I didn't tell you which mu. We have two types of mu. We have a mu k and a mu s. This is static, this is kinetic. Motion, static. Now in this case here, which one I need, a mu s or a mu k? Why s? S is static, not moving. K is moving. So mu k, you agree with him? Mu k? Okay, it's not right, it's wrong. Look, which friction you're talking about? This friction or this friction? Do you have motion sideway or static? If the car on the roundabout, it doesn't slide off, yeah? So here you need a mu s, not a mu k. Static. Kinetic is not responsible for the circular motion. Kinetic is opposite motion. But static this way. The car is not sliding off. So now let's discuss this equation. Suppose you've been given a project of designing a roundabout. As an engineer, you'll design roundabouts. And the roundabout which you have to design is unbanked, leveled. And they say, okay, this roundabout, which you have to design, it must have a radius of 10 meters. 10 meters, small one in the residential area. So if the radius is 10 meters, according to this equation, G 9.8, yes? Around 9, let's say it's 10, for sake of argument. And mu, this is between the tires and the road, yeah? And let's say you have the best tires, brand new, and the road is so rough. So mu is maximum. What's the maximum value? 1. So let's say mu s is nearly 1, and G nearly 10. So if the radius is 10, what is the speed equal to? 1 by 10 by 10. So V equal 10 meter per. What does this 10 mean? It means the roundabout which you design, or the bend which you designed on the road, it allows cars with a maximum speed of anything more than 10, and you enter, the road will tell the car that FC is not equal to FR. They are not equal, which means this side is not equal to this side. So the what happens? The car will look for a bigger radius. This is the radius given, 10. So if you come with a speed more than 10, let's say 15, for 15, if you put 15 here, it gives you a velocity more than 10. So when you come with 15, 10 is not enough for the car. So your car will slide to a bigger R. Once it reaches this R, then it has a new circular motion, a new arc. Yeah? But of course, this will be, by the time the car finds a new radius, it's too late because you already crossed the pavement, hit the trees, you have an accident. Yeah? Bigger radius means you are off the road. Now, this is not dangerous if you are driving in open space, yes, and the road is flat. You can try this out. When you're driving out, 10 suddenly to the right or to the left, sharp radius. You're coming at high speed. Sharp radius means the radius is small, but your speed is. So the FC and FR not equal for this small radius. So what happens? Your car will slide off, looking for a bigger, until it reaches that radius, then it continues the arc. Yeah? Of course, the condition is that nothing there. Huh? So you don't have an accident. Open, yeah? Open area. So what do you feel when you do this? You feel as if you've been pushed off the center, yes? But this is not a true force. I know that you learn in the schools that there is a force off center. Yes? Didn't you learn this in the schools? They told you that when there's circular motion, there's a centrifugal force. Not centripetal, centrifugal. This is not a real force. This is not a real thing which you experience. We call it fictitious force. You imagine that there is a force this way. In reality, there is no such a force. The only real force is towards the center, not off center. So what happens here? The car was looking for a bigger. Okay, it's not like it's being pushed. No, looking for not a real force, fictitious force. Until it found that one, then it continues. I'll come back to this point later on, explain the centrifugal force. But what I want to say that there is no such a thing, force off center, force towards the center. So did you understand this point? That what does it mean? This so this equation gives you the speed limit. Which means in this road, if you have a roundabout of 10, what do you put here? A sign saying what? What's the speed limit? Of course, you have to change this one to kilometer per hour. Easier. Multiply by 3.6. This is the speed limit. Any speed higher than this, slide off, yeah? Is this a good design of roads? Not a good design because it depends on the friction, yeah? So if I don't have friction, let's say mu, very old tires, and the road is not rough, smooth. When you turn the car, will you be able to? Or slides off, yeah? So the engineers, they thought of a new design, which doesn't depend on friction, okay? Or when the tires are old, this will go down, like 0.1, yeah? So the smaller the mu, the smaller the maximum speed, yeah? So you have to come slower to avoid sliding off the center. So the engineers, they come up with a new design of roads which doesn't depend on friction. Remember, friction here is possible, but in Europe, when it's cold, they have ice and rain, always friction is minimum. So they cannot depend on a friction to turn. And then you'll have a traffic jam each time you have a bend on the road, on the highway. You want to keep on at the same speed when you bend, when you go to the right or to the left. So they came up with the designs of roads which is called banked road, not unbanked. Banked road. What does it mean, banked road? This is the word bank comes from bank of a river. You know the edge of the river? It's not flat, banked, slope. So instead of having a leveled road, when the car turns to the right or to the left or on a roundabout, the road is banked. Like you have this experience, this feeling on the roundabout outside. Any roundabout, you feel that it's tilted to the inside, yeah? The outer side is higher than the inner, like a slope, to the right or to the left. This is called banked road. How does this one work? Now, let's look back view of a banked road from the back, and you cut it. So what do you see? The road is like an inclined surface. And this is the theater, and the car here on the bend. And this is the bend. This is like you look side from the back. You see the car, and the car is doing circular motion. And where is the radius? This is the car. The center here is in space. If I show it here, I'll create a bank road here. This is an unbanked road, yeah? This is the car. Now this is a banked road, yeah? Angle. This is part of a roundabout. So when the car on the bend, and this is the center is not here. This is the circle in space, yeah? Doing this. We have a circular motion now. Now circular motion needs what? A centripetal force towards so I need a force towards this point. I have to think of forces on the car here. I have to put all the forces and see which force is towards the center. And if I find the force towards the center, that is what? The centripetal force, which keeps the car going around. If I can't find one, then the car will not turn around, yeah? So let's think of the forces on the car. Remember, there's no tension. This is just to keep it in the radius, yeah? What are the forces on the car? Let's do it on the board. If you have an object on an incline, what are the two standard forces? Fg and normal, yeah? So Fg, perpendicular on the ground, and normal perpendicular on the surface. Yeah. Now, where is the circle? It's here, in this plane. And this is the center. Is Fg towards the radius? No. N towards the radius? No. Any other forces on the car? Okay, good. He said the friction. But remember, I want to design a road which doesn't depend on. So in this road, frictionless, zero friction. Okay? Now, if you remember before, when you have an object on a slope, where did we put the x-axis? Parallel to the incline, yeah? And the y-axis, perpendicular. Why we put the x parallel? Because we had a motion up and down, yeah? But here I don't have a motion up and down. I need something on the circle. So the best way is to turn the x and y and put it as we usually put it. X is horizontal, y is. Don't mix this one with chapter 5. Chapter 5, you put x here. So here now, I put the x-axis in the direction of the radius, horizontal. And the y-axis, perpendicular. Now, look now. Fg has component? No, on the y-axis. Where is n now? Has component in the second quadrant. Now, by geometry, if this is theta as well, with the y-axis. So n will have two components. One on the x, what is it? N. And one on the y. And I don't need n. Now, do I have a force towards the center or not? Any other forces towards the center, or this is the only one? So this is Fc. Which means for a bank road, we say Fc is equal to n sine theta. So if you've been asked, where does Fc comes from on a bank road? what would your answer be? Name the force. If you say just component, is wrong. The horizontal component of the normal force. If you say normal force, is wrong as well. Normal force is not in the direction of the radius. So the x component or the horizontal component of normal force. Now this is for the x-axis. For the y-axis, what do I have? Equilibrium, yeah? N cosine equal Fg. So if I put here Fg equal N cosine theta, equation number 2. Now here we have two equations. When you have two equations, one with sine, another with the cosine, and you want to solve it algebraically, the easiest is by dividing the equation, not by elimination or by substitution. Why? Because if I divide the first and the second, what I'll have? Sine over cosine. So I'm replacing 2 to 1, yeah? So here you divide, and be careful, divide 1 over 2. Suppose you wrote this one first, this one second. Don't divide 2 over 1, you'll have cotan. You need sine over cosine, not cosine. Now, FC divided by FG. This is the division of this side. And this one, N sine theta over N cosine theta. Normal is not needed. Okay, so we'll have FC over Fg equal tan theta. Now, what is Fc equal to? mv square over r. Fg here, mg in general. So this equation becomes mv square over r over mg equal tan theta. Again, as before, do I need the mass? The mass has no effect on the circular motion. What's the final here? I can say that tan theta equal v square over rg. But if I want to compare it to the unbanked road, how did I write? V equal, yeah? So let's write what is V equal here. What is V equal to? Rg tan theta. Look at the beauty of this equation. Remember, V means the maximum speed, yeah? Safe. The maximum speed on the bank road, does it depend on friction? No. You don't have friction signs. No mu, no Fr, yes? Depends on what? Radius of the road. G constant. But now you have a new factor. The angle of the road. So, if you want to maximize the speed limit, what you have to do? You have two factors. Either you increase the radius of the bend, and you know that the bigger the radius, the safer. You can come at high speed, but don't turn sharp. Turn sharp means small radius or big? But if you take big radius, do you have to slow down? And it's still safe, yeah? So the bigger the radius, the higher the speed limits on that road. The second, you can change the angle of the road. The steeper, the better. The higher the speed, maximum speed, yeah? And that's why on Olympic games, cycling, you've seen those, they go around on a steep road, yes? The road is shiny. No friction. And they go around very high speed and they don't fall, yes? Why is that? Because they depend on this equation. It's a bank road. And in bank road, do you need a friction to do circular? So it's safe. Even if you have ice, snow, still you can turn safely, but your turn will depend on the component of the normal force from the road. Yes, Rami?
What if there is friction?
That friction is not an advantage here. Friction will work here. Up and down, up and down. No. Friction is not a vector. Friction force is the only, I was going to mention that friction force is not a vector force, because vector means it has a specific direction, yes? But friction, you put it at the end, depending on which way you want to move. So sometimes you move this way, it's this way. Sometimes you move that way, opposite. So it doesn't have a specific direction. It's just opposite motion. So you don't treat it as a vector. Don't treat friction as a vector. But anyway, if you have a friction, how it works? Now, friction will be an advantage if you come at very high speed, which means the radius which you have here is not enough, yeah? So what happens? Your car will slide up. Why? Looking for a bigger? But when it wants to slide up, if you have friction, will hold it. And if you come at a smaller, of course, if it wants to slide down, friction will hold it up. So it works both ways. That's a bonus. But it's not responsible for making the turn. You don't need a friction to turn. But here, you must have friction to turn. Otherwise, you can't. So if you are designing a road, if you are a civil engineer, we have civil engineer here, yeah? And if you have a project of designing a bend on the highway or a roundabout, keep that in mind. You have to have it banked, and then you ask for specifications of the road. What's the radius needed, and what's the angle of the road? Now, if you have the freedom of designing, will you choose a big radius or high angle to increase the speed limits? Now, both. That's when you have a lot of money. You don't care about the cost. Engineering is about cost. Each time you design something, you have to think of how much it costs. This is a road. You think it's easy to make a big angle? Now, when it's easy to have a big angle, if you already have a land which is a bit higher from one side to another, so you use that to make it steeper. But if it's flat, you have to have more soil to make a mountain, okay? And this costs money. I'm just saying, will you think of making a big angle or big radius? Now, if you want big angle, of course you can have big angle, but when you use big angle, if the terrain itself, the region, it's not a flat, you have a part. Like you have a part of a mountain, you just have to cut it. So it doesn't cost you a lot, yeah? And you have a bend. But if you have a flat area, you can't. You have to create a mountain, yeah? And this mountain is not just one piece, it's a bend. Depends on the radius. Now, sometimes you must use big angle, but small radius. Why? Suppose that your highway goes through a town, small town, yeah? Now, if it goes through a town, can you make a big bend, big radius? Big radius means when you want to design the road, you have to demolish some of the houses, yeah? Big area, because you're taking a big arc. You're taking a bigger piece of land, and that costs money as well. So it's a balance between those two factors. Think of these two in your design. Which one is more suitable, doesn't cost that much money. So this was the second example, or third example. I gave you tension, horizontal, and bank road. Bank road. Now, the third example of horizontal circular motion. Conical pendulum. Conical pendulum. What's a conical pendulum? You're all familiar with this pendulum. What's the name of this pendulum? Is this a conical pendulum? No. This is called simple pendulum. Simple. Now, how do you create a conical pendulum? The word conical means cone. It's the same. Bring a simple pendulum, displace it sideways, but don't let it go back this way. Push it sideways. What do we have now? Circular motion, yes? Horizontal or vertical? Horizontal. And what's the shape? Like a cone. Yeah? This is the tip of the cone. This is a circular motion. So now we have to study this motion and see where does FC comes from in this shape, yeah? So I'll draw it here. Let's say this is the ceiling, and this is where you hang the pendulum. This is the lowest point, straight. From here to there is the length of the pendulum. Now, how do you generate a conical? You push it sideways, so this point will go up. And what is this now? Still L, yeah? Same length. But the point is up. Then you push it sideways. So where is the circle? This is the center. And this is the radius. And then it does, let me remove this part there. You'll have this cone. This is the center. So what do we have here? An angle theta, and this is the same angle. Looks like a little bit bigger. So you can see we have a cone. And this is the circular motion. It could be here or here. And from here to there is the radius. And of course you have radius this way and this way. And all this from here to there is L. This is to the lowest point. You imagine the lowest, but there's nothing here because the pendulum is here. So I just remove this just to tell you this is the lowest point. Right. Now we have a circular motion, which means we must look for at least one force towards the center. What are the forces on the mass here? How many forces do I have? Two. FG down and tension not up, tension in the direction of the cable. F tension. These are the two forces. Now we need a free body diagram, yeah? On the center of mass. So if I put X and Y here, which force has component? FG or FT? FT. Now, by geometry, if this is theta, where is theta? With Y, yes? And this is FT. Let's remove this one. And from here to there is L. So FT has component, two components. One this way, what's the name? FT sine theta, and one upward, FT cosine theta. Now you can tell me that. Which force is responsible for the circular motion? FT, the horizontal component of the tension force. So here we say FC equal FT sine theta. Equation number one. Now for the y-axis. Force up, force down. Does the mass go up or down? No. Equilibrium. So what do we have here? Fg equal F tension cosine theta. This angle theta, the vertical angle, when does it change? Okay. When does it change? When I increase, but how do I increase the radius? If I make the speed higher, if I speed it up, what happens to the theta? It goes up, yeah? If it's slow, down. So the radius will go down, yeah? So the higher the speed, the bigger the angle. But the angle does not change at each speed, yeah? Constant speed, stay, the angle is the same. So the angle is fixed at each speed. Now, what shall I do to equation 1 and equation 2? Divide them. So I'll have FC over FG equal FT sine theta, FT cosine theta. FT is not needed. FC is mv square over r. FG is mg. And this becomes tan theta. The mass has no effect. I'll end up with the same equation or not? Yeah. What is the same equation? Tan theta equal v square over rg. Yeah? And write it in terms of v. I'll write it here now. V equal root rg. Okay. Surprise, surprise, is the same equation, yeah? But how you look at it is differently. Yeah? When you talk about a conical pendulum, how do you interpret this equation? V for the pendulum, the conical pendulum, speed of rotation. R is the radius of the pendulum. Theta is the angle of the pendulum. Yeah? But when you talk about bank road, how you look at the equation? R is the radius of the road. Theta is the angle of the bank. Same equation exactly, but the way you look at it is different. Right? What else do I need in a conical pendulum? Some geometry here. Look at theta, L, and R. What's the shape? Triangle, right angle triangle. This triangle here. So this triangle, this is theta. From here to there is the length of the pendulum. This is the mass here. And from here to there is R. This side, be careful. This is not the length. This is, let's call it H. This is up to the center, from here to the tip. H, yeah? Now, if you add to H the distance from the center to the lowest, if we call it Y, so here, if I just add it, Y, from here to there is the length of the pendulum. Now, in this triangle, what are the equations I can generate? Sine, cosine, and tan. If I say tan theta, what is tan theta equal to? R over what? H. But do you know H? Usually you don't know H, yes? So tan is not useful because you don't know H. And to find H, what do you need? Y and L. But if you say sine theta, useful? R over L. And R is the radius needed. And L is the length of the pendulum. What about cosine theta? H. This one sometimes is not useful because H, yeah? But in some other context, we need H. But anyway, for a conical pendulum, you need that equation and this one. By the way, this equation will not be given. This is a concluded. All the end equations are not given. So you have to find them yourself. These are combinations of equations. Right, this way I covered all the examples on horizontal circular motion. What I'll do now, I'll give you one more on vertical, and next time we continue. Okay, so I'll just move to vertical circular motion. Vertical circular motion. Now, if you remember at the beginning of the class, I said that when we have vertical circular motion, we have to include the force of gravity. Now, if I do circular motion now, vertical, the plane of circle is in the plane of gravity. So gravity force has an effect on the circular motion. Yeah? Now, in circular motion vertical, the motion is a little bit more complicated than the horizontal. Why? When the object is at the lowest point, bottom is easy, and at the top. But when it's in between, you have components, yeah, of forces. So what we'll do here, I just concentrate on the case when the object is at the bottom and at the top only, not in between. If the object is not turning at the lowest point of the circle now here, how many forces do I have now in this example? Two. What are they? Tension which way? And? Now, do I have motion now? So what do I say? Equilibrium, yes? Tension equal Fg. But when this one turns at the bottom, you can't say tension equal Fg here at the bottom. Why? Because you need a total force towards the center, Fc. If you don't have a total force towards the center, then you cannot generate circular motion. So when this one turns, do you think Ft equal to Fg or not? No. Which one is big? The one towards the center. So at the bottom you have F tension minus small equal Fc, the net. So here we have two forces, one towards the center, one off center. What's the total towards the center? Big minus a small equal Ma. So I'll draw it here for you. And vertical, put the ground like that. So when you draw the circle, it looks like vertical. At the bottom here I'm using the example of tension. We'll change it later on. This is the center. I have a cable. Which way is the tension? Up. Gravity. Now, which one is big? Always towards the center, Fc. So here we say Fc, the net, big, Ft minus small. They are not equal. And what is Fc? mv square over r. Tension force minus mg. When do you use this equation? At the bottom. Only here. This is your equation. Now, think of the top point now. Here. What happens now? Which way is the tension? Which way is the cable? At the top. Down, yes? Tension down. Which way gravity? Down as well. How many forces do I have towards the center? So what's the total? Fc plus Ft. So at the top point, I have Fc is the summation of these two. Fg plus Ft. And Fc is mv square over r. And this is mg plus Ft. This one for the top points only. Okay? That's it. This is an example of vertical. Later on, we have more examples on that. Yeah? So now you can start on the review problems. Do as much as you can, because next week we'll have exam number 2 in chapter 5 and 6. I finished nearly chapter 6 now. Next time I see you, just do problems. So it's not a long one, okay? So this is the end of the class, and we continue next time. Thank you.